let's start. Happy to be here. This is my second time in DEF CON and second time talking on the creator stage. I'll be talking about a mix of my favorite topics, which is network fingerprinting, honeypots, and AI agents. So I kind of mixed them all together and created an open source tool just a few weeks ago. I released it last week. And yeah, I'm gonna go through why it can be useful and how you can probably use it for different use cases. Because usually I start with a fun, crazy idea which doesn't have any production use case, and then it turns out that, okay, this is useful, maybe I should release it to the rest of the world. It was the case with this one as well. So before we get to the slides, just a quick intro. I'm Adel, working on security detection and response for over 10 years now. Part of it in Google, and now at a AI startup, AI chatbot startup. And yeah, outside work, I just work on random honeypot projects and things that I can easily release without getting approval from the company. So yeah, I don't want to be known just by honeypots and network fingerprinting, but that's the easiest thing to publish. I have a bunch of open source projects. You can take a look at my GitHub repo, 0x4d31. That's my Twitter handle, and also GitHub. I have a QR code and all at the end of the slides, so if it didn't work, I can just show you on the slide on my MacBook. Okay, so the initial motivation and why I created this thing. So what is even this thing we're going to talk about? So it's basically a fingerprint-based or fingerprint-aware reverse proxy. This is just a term I made up. It's not a known term. So if you don't know what it is, that's fine. So the idea was to see if I can mess with the attackers based on their client fingerprints rather than just IP or user agent and things like that, which can easily be faked. So I have a quick primer on the fingerprints and how they work. So don't worry if you don't know anything about the fingerprints. But yeah, that was the idea, just to have a more intelligent way to waste attackers' time or dynamically route them to different systems or different honeypots and things like that. But why at the reverse proxy level? Why not just a passive system like Suricata or Zeek to just capture all these network fingerprints? Basically, I started from there. Like a few years ago, I had a talk about Honey TLS, which was just a very janky Nginx SSL reverse proxy, which I kind of used as a honeypot. And I collected these TLS fingerprints and other network metadata using Zeek. It was Bro that time. And yeah, just my goal was to see if we can find more interesting patterns looking at these fingerprints and extra metadata rather than just looking at the source IP, user agent, and the request. Because if you attended some honeypot talks before, you see that all you get is just oh, I set up this honeypot and I got these 100,000 requests in a day. It was the top request was from this country, these ports, and these requests, and that's it. So 7 years ago or 8 years ago I was working on this Honey TLS thing. I captured logs for about maybe 3 months. And then I had this talk at the HoneyNet conference. As always, I was creating the slides and looking at the new data just a night before. And then I found a really, really interesting pattern in the logs, which I will hopefully show you later in the slides, which kind of proved that how useful these extra metadata is. So even if you don't want to use this as a kind of a signal or as a mechanism to route the traffic to other systems, you can just have this as an extra metadata or signal for your analysis. It would be very useful for the threat intel stuff. And another reason that we do this at the reverse proxy level is, so with my previous setup, I was capturing these connections with Zeek, as I said, and you get just the TLS handshake at that level. You don't get the HTTP logs. So I had to collect the HTTP logs from the honeypot, which was the Nginx I mentioned, and I had to join it with the TLS logs to get something useful, to have both HTTP and the TLS stuff there. But if you do this at the reverse proxy level, you just get that automatically. So you just have both TLS stuff, the HTTP stuff. It would be way more useful. You can also have the HTTP fingerprints in addition to TLS fingerprints as well. Okay, so another reason I was thinking of using fingerprints, and maybe it's useful for you as well, is relying on IP addresses and user agents or things that can easily be changed or faked is, just a second, maybe my slides are recorded, so I can move on the slides as well. Yeah, so the reason is IPs and user agents can easily be faked. And so they just rotate IP addresses like 100 times per minute. And if you set up like honeypots before, you see that like you get like a lot of requests from different IPs, different ranges, but they all seem to be from one actor. You can't really prove it unless you have these additional data, which is like the fingerprints and a few other things. So instead of relying on user agents for blocking bots or crawlers or things that you don't like, or just going after this like whack-a-mole of blocking IP addresses, you can just rely on extra things deeper into the packets. So for TLS, it's TLS handshakes, client hellos. And for HTTP2, there are these extra frames like settings and update window and priority that you can use, which is very unique for different clients. And even for HTTP itself, just like the order of headers are really cool. Like it can easily be faked again, maybe a bit harder than user agents, because like, for example, if someone uses like Python request, it always comes with these 3 headers in the same order. So they can change it, but it takes a bit more effort compared to user agents. But yeah, once you have these metadata or fingerprints, you can block easier and smarter. You can deceive better if you're into honeypot. And you can find patterns that otherwise would be impossible to find. I will show you some very interesting patterns which I found using these fingerprints. So just a question before we go further. Can your WAF currently, like whatever application firewalls you're using, or like AWS, whatever edge service that you're using in front of your like production services, allow you right now to block things like Zap or Burp Suite or like other tools like that? No. I know like a few providers like probably AWS and Cloudflare provide something like that, but it doesn't let you customize things and say, like, for example, I don't want to see traffic from this specific TLS fingerprint. They just apparently have this like checkbox that you can say, okay, protect me from known bad bots or things like that maybe. But yeah, so because of that, I thought, okay, it might be interesting to just set up like create a new reverse proxy. My intention was not to build something like huge from scratch, like Nginx or Caddy or things like that, because those are way more complex, harder to customize and things like that. But I wanted something very simple for my use case. And so yeah, that's why I started building this tool. You can even do very fun things that I'm sure none of other web application firewalls and those cloud-based services can provide, such as redirecting the request based on their fingerprints to honeypots, or deceiving them by some other methods, or targeting them, like slowing them down. Okay, so at this point, we know most WAF don't do that. So that was basically the reason. So Finch, this tool I released last week, is a fingerprint-able TLS reverse proxy that lets you deny, route, target, and deceive based on those client fingerprints, and also other like basic metadata, like the request and the user agents and the other HTTP methods. And even something I added, just remembered, was Suricata alerts. So without relying on the Suricata service itself, I added this like parser for Suricata HTTP rules. It doesn't support all the keywords and all the complex things, but it works for my use case. So you can just like download the Suricata rules, like put it there, enable the Suricata module, and then all the requests coming will be matched against those Suricata HTTP rules as well. And then it will be exposed into the tool configuration as well. So you can decide to redirect traffics or block based on the Suricata message as well. So you can say like, okay, if it matches with exploit message in the Suricata, just block it or redirect it to honeypot. Okay, so in the slides, I had this example for Zap web application scanner that I will show that you can customize the user agents from the tool setting, but that's it. Like you can't change anything about the order of HTTP headers or TLS or things like that. So you could just use these fingerprints in this easy to use HCL configuration, which I have in my tool, and block these. So for the configuration, you can't see it, but it's pretty similar to Terraform configs. So very simple. It's not that messy compared to the other reverse proxies, which like it's always like when you change something, it breaks everything, and it's either like these complex JSON or like YAML or things like that. But yeah, I decided to go with, I did like a few iteration, and at the end I came up with the custom HCL one. Okay, so at this point in the slides, I will show an example for the Zap scanner, which can slow down the attacker. It does the targeting. So whenever someone uses Zap to scan your application, it slows down. And for example, an scan, which normally takes like 20 seconds, like I tried it with Nmap as well, it takes more than 10 minutes to finish. So you can just waste attackers like time or resources that way. I mean, it kind of wastes your resources as well, but I put some guardrails and protections and limits. So there can't be, for example, more than 16 simultaneously open connections to your proxy. You can customize that. Okay, so before the fun part starts, we need some basics about the fingerprints and how it works for the people who don't know what it is and what we're actually talking about. So where these signals like you can find, like where are these signals or entropy we're talking about? So as I mentioned before briefly, in TLS you can look at the TLS handshakes, and although like TLS is encrypted, but like that initial handshake, especially client hello and server hello, are clear text. So you can just look at that, extract those parameters, and those are very unique for different libraries and clients. It's not a silver bullet. Like some people I've seen that use it as a signature for writing detections. It doesn't work well in that use case. I mean, there are a lot of command and control like C2 agents and implants that use very specific TLS configurations, which is very unique to them. So in those cases, you can use it for like detecting those if you have any network monitoring tools like Zeek in your network. But in other cases, I don't suggest to use it as like the only detection method, because it would be very noisy, false positive, false negative, and things like that. So I suggest using it just as another data point. So just something beside user agent and other metadata you have from the networks, just add this as well, which help you find very interesting stuff. For HTTP, as I said, the headers and the order that those headers appear is where you should look for. And HTTP2, same, like there are some frames like settings, updates, and priorities, which you can use for these fingerprints. So in TLS case, we'll start with TLS. In the client hello, we have multiple parameters. One is version, the other one is cipher suites, and then extensions. These extensions and cipher suites usually come in a very specific order. again, these are things which depend on the underlying library that the client uses. So for example, if Google Chrome uses Boring SSL and another tool uses the same version of Boring SSL on the same OS, you probably get the same fingerprints for both too. But it's nice. Like in some cases, you see some very unique things, especially if you combine that with other things, like for example in HTTP, as I mentioned. That's why I really like to do this at the reverse proxy level, because you can then cross-check like the HTTP fingerprints and info that you have with the TLS ones. So maybe the attacker tries to fake the TLS and forget about the HTTP, and vice versa. So then by checking these two, you can say like, oh, this like pretends to be Google Chrome by looking at the user agents and fingerprints. But then you look at the TLS stuff, it's like, no, it's like a curl, for example, or some other random tools. Okay, so I just skipped these slides because you can see that it's just a bunch of screenshots for TLS packets and handshakes, which shows where these versions and crypto algorithm exist. I will just share after the talk my slides in my GitHub repo, so you can just download and go through them. So one of the most common fingerprint techniques is jaw tree. You may have heard about jaw tree. There's been a lot of TLS fingerprint and similar work like in the past like 10 or 20 years. So this is not just a very new concept or thing, but it was very hard to use those previous fingerprinting techniques because it was not easy to share them or use them in the different tools. There was no support in different, for example, security products. But jaw tree, created by one of my former colleagues back in Salesforce, is a very easy one. It's just a hash that combines versions, ciphers, extensions, curves, and elliptic curve format in a specific format, combine them together and create a MD5 hash on it. There's been also some like issues with it because, like for example, some legitimate tools like Google Chrome browser, they have this extension called Grease, which just randomizes these extensions, which kind of mess with these like jaw tree fingerprints, because like if you capture traffic from Google Chrome, you see that, oh, it generated like 20 different jaw tree, and that's why. But generally it works pretty well, especially if you also log the raw strings before applying the hash to, because like the raw string, when you just put all these parameters together, it kind of shows you some interesting patterns which the MD5 one doesn't. Because like looking at an MD5, you just see a random packet, a random string, which doesn't mean anything. But looking at those raw strings before applying the hash, you can actually see like, oh, this was like TLS 1.2, or this was like the list of cryptos and stuff. And that's why he created like the next version, which is JAW4. So in JAW4, it's more readable, like rule friendly. You can just like, for example, write a rule to look for the first like few characters and then asterisk the rest, because the format is defined in a way that's easy to do that. And just by looking at the string, you can say that, oh, this was like a quick traffic, or was it like TLS 1.3? And then you can see the rest of things as well like that. So it's way more readable, and it's resilient to that Google Chrome randomization thing, as I mentioned, because it doesn't store the ciphers and algorithms in the order that they appear, but they actually like sort it and then generate the hash. So it solves that problem. Okay, one quick other thing about like TLS, and then we move on to HTTP and other fun stuff. So Quick is this protocol, which is like TLS 1.3 over UDP. I suggest like searching about it, because like majority of web traffic right now is on Quick, and it's not like the normal TLS over TCP traffic anymore, especially if you use Google or Cloudflare or websites before behind Cloudflare. You have this Quick thing, which there's been a lot of different versions. Google started that, and then IETF standards did some standardization to make it available, like to other people and folks. So the thing is, most of network monitoring tools are currently blind to this traffic. Like there are no parsers for Quick. Wireshark has some modules. By default, you don't need to install anything. So just spin off like Wireshark, search for Quick, and you will see the traffic. So the interesting thing about Quick is it's not like the normal TLS traffic, which you can just look at the traffic and extract the TLS handshake, like the client hello. The problem with Quick is that TLS client hello is protected by some encryptions, which can be recovered and decoded. So it's not created, so no one can look at that. It's a specific standard that if you know it, you can decrypt and extract that TLS client hello inside it. So the thing I did, I add some experimental supports of Quick to my tool. So I tested with curl, it worked, but with Google Chrome, it didn't work for some reason, so I need to fix the problem. But anyway, this is just like an experimental thing which I added support for, and it's cool. So even if you have like HTTP 3 Quick traffic, you can do the fingerprinting, applying the same JA3 and JA4 fingerprinting to those as well. So I also included a client tool, which you can use. It's in the repo, that it monitors the Quick traffic or the PCAP, and it extracts these fingerprints from the Quick traffic. Okay, so for HTTP, as I said, I really like HTTP 1 because like it's very simple and it's very effective. Like it's a very hard, strong signal for a lot of clients. Just looking at the headers and the order of them, like that's it. Like I was using this for many years in my other open source tool called FAT, which is like fingerprint all the things. It just collects metadata, and I had this very simple HTTP fingerprinting based on just the headers and the orders. But if you want to have something like more standard, JA4 also have a HTTP version called JA4H, and I added support to my tool as well. So just out of the box, you see JA4 beside the JA3 stuff as well. It's a bit more than just headers and the orders. It also captures some cookies and referrers and things like that, which you can specifically identify one specific clients or application versus like just in general Google Chrome version X. And the last one in the list of fingerprinting 101 is HTTP 2, as I mentioned. I don't want to repeat it again, but there's this method which someone from Akamai worked on, which combines settings, window update, and priority, and creates this like fingerprints, which I also really like because combination of these HTTP to HTTP and like TLS gives you a very strong signal about the clients. Like you can do way more reliable fingerprinting based on those. And before we end this section, there's this part about evasion techniques. So as I mentioned, of course, these fingerprinting techniques are not like bulletproof. There are many ways attackers can like fake these or mimic, for example, a specific known client application by just changing the way they create these clients. Hello, for example, for TLS. It's interesting, like a similar talk I had like 5 years ago, there was no known tools. There was just one called UTLS. There's this library that you can use to fake HTTP TLS fingerprints. But now, like just before the talk, I was searching to see if there are any new tools, and there are like tens of other new tools because a lot more people started adopting JA3. Like now JA3 and JA4 is supported in like AWS, Cloudflare, many tools like Suricata and Zeek and other open source and commercial tools. And because of that, now they know the value of these fingerprints for defenders to detect bots or specific tools. So now they started using these mechanisms to fake them. But even that, as I said, like one thing you can do is to just have multiple layers of fingerprints, HTTP, TLS, and a few other things. And it would be way harder to fake those for the attackers. They would probably miss to do like all of those because they already know that a lot of companies don't even collect like jaw trees. So yeah, they don't care. Like they just like maybe less than, I don't know, like I don't have a number, but less than 10% even know about these jaw trees like on the offender side. And yeah. There was even one I found which was very interesting because one of the demos I had was I was fingerprinting Burp Suite repeater module. So if anyone wants to use like Burp Suite to scan your website, do some bug bounty hunting and finding bugs, you can just block them. I mean, don't do that unless you're a very broke startup or you don't have like resource to fix your security. Like, I mean, blocking security scanners is not the solution. But there is this module in Burp Suite called Burp Awesome TLS, which you can install and fake the TLS fingerprint of the Burp Suite as well. It's nice. Okay, at this point, I definitely need to have some slides. Otherwise, I can just show you the slides like this. Or something I could do was just to share these so you could all just look it in your phone. But I guess I will do it after the talk. So I have this graph, which is really nice. It shows how by just adding these fingerprints to the mix, you can uncover some very interesting patterns which otherwise would be impossible to find. So what I did was when I set up my Honey TLS project, I collected TLS fingerprints, as I mentioned. So I started visualizing these, creating some directed graphs with D3, and the pattern was very interesting because I was expecting to see like the source nodes are source IPs and the destination nodes are these TLS fingerprints. So what you expect to see is usually seeing one jaw tree fingerprint with a lot of source IPs around it, right? Which means someone used Nmap and okay, a lot of other people use the same tool as well because it's a known tool. So the fingerprint is the same and a lot of IPs used it. But what I saw instead, I mean, 80–90% of the traffic I saw was following this pattern. But there was this very interesting pattern from 3 or 4 actors, which was like one IP address generating hundreds of jaw tree. And it was interesting that this pattern was even unique to those actors. So when you were looking at this, like actor X, for example, you were looking at the raw jaw tree fingerprints, like before adding the hash. You were scrolling. I mean, that's how I found it. It was very accidental before a talk. I was scrolling through this sheet, which contained the raw jaw tree strings. And I found something very interesting. My eyes was like, oh, there's a very interesting pattern here. When we were scrolling, there was like this line, which was like, I had sorted it based on time. So you could see that one IP address changing, like for example, removing one algorithm from the mix, the next one remove another one, in the next request, it removes another one. So it was doing obviously some sort of randomization or like rotation to avoid TLS fingerprint-based detections. And it was interesting that this actually made them more obvious because after I visualized this and looked at the pattern, I was like, oh, these 4 things stand out. But probably a lot of other people didn't notice because they were not collecting these fingerprints. And yeah, so another interesting thing was a lot of these IP addresses was completely in different ASNs. They had completely different identities and everything. And without these TLS, there was almost impossible to create some connections between these. But what I saw was like, especially for one of them, there was this cluster with like IP address and 100 completely unique jaw trees. And the same for 4 other source IPs. And the only way I could connect these 4 clusters together was that they apparently, by mistake or something, they all 4 used 2 or 3 common fingerprints. So that common fingerprint was in the middle, and it was connecting these 4 clusters together. So it was a very interesting observation, which you could only do having these fingerprints. So let's just move on to the actual, talk about the tool. So as I mentioned, I released this tool last week. You can just go through my GitHub 0x4031/Finch and just start using it. It's based on Go. It collects these fingerprints and other things and expose them into the rules, so you can decide what to do with those traffics based on those things that you collected. So basically collect, decide, and act. You can just block, do whatever you want with it. So, demo time.
Great demo, well done.
I will upload the videos as well because there are like really interesting ones. Yeah, so one of them which is more interesting, which is the deceive action. So I have these 5 different actions in the tool: allow, deny, route, target, and deceive. So the deceive action actually just made up HTTP response on the fly using LLMs, because like why not? Like let's say you have a request receiving in your reverse proxy to a path that you don't know what it is, like you don't have any production servers behind it, or it maybe matched some Suricata alerts or something, and then you want to just redirect these to, like you just want to respond to that, but you don't know how, because maybe it's just even like a 0-day exploit or something, so you don't know how to respond to / shutdown, for example. So what I do is I use this tool, which I released last year, like the talk I had last year here was about that, which is a LLM-based web honeypot. So instead of having the honeypots generate like with static responses, I asked LLM to generate the HTTP response, and it works pretty well actually. I didn't expect that, but it works pretty well. Even if you don't use smart models, and it just generates the response less than a second. So what I do is I exposed this project called GLA as a service. So now I use this service in Finch. So whenever you use this deceive action in your rules, it just calls GLA, it passes the HTTP request, and it waits for the LLM to generate the HTTP response and then give it back to the attacker. And I mean, you may say like, okay, why do I need to spend money on responding to attackers? I mean, you can just use a very cheap LLM model. And another thing you can do is to enable caching, because I added this caching thing, which like when you first generate a response to a specific path, you don't need to do it again using the LLM the next time. You just use the cached one. But I even did something else just like a couple of days ago. So I leaked this fake LLM API key in a fake code snippet with fake custom OpenAI endpoint in Pastebin. And just a few minutes later, a bot took that, reached out to my Finch proxy with that fake API key. And what I did was to respond to that using a Markov chain-based junk response generator. So I didn't pay anything for that. This is like the simplest way if you don't want to use LLM. Again, more demos, more examples. I have these example, like I just pushed these example fingerprints to the tool repo containing real JA3, JA4, JA4H fingerprints for some known tools like Zap, Nmap, and Burp Suite. So you can just try that on your own. The tool also comes with admin API. So that's actually where makes this reverse proxy smart. And like you may ask yourself, like, okay, where was the thinking part in this like reverse proxy? That was like the title of the talk. That's actually starts from here. So I exposed this admin API to the reverse proxy. So you can just programmatically update these rules you have in your reverse proxy. So I added an AI agent on top, which constantly monitoring the logs that you generate, like the reverse proxy generates. And if it finds something interesting, like a pattern or something, it automatically updates the rules. So yeah, that was one thing I added, and there's also this SSE endpoint which streams all these events. So if you don't want to use the JSON log that the tool generates, you can just use this SSE endpoint which generates these logs like real time. And I have an example client for that in the repo as well, which is very nice. You can just like look at that and search and filter the logs. There's an echo mode. So if you want to generate a data set of fingerprints, you can run the tool in echo mode, like Finch space echo, that's it. And then if you hit the root, you will see like a nice like UI showing you all those fingerprints for your client. If you hit like /fp, you get the raw fingerprints in the JSON format. So where this would be interesting is if you, for example, want to automatically generate the database of fingerprints. So you just create a tool which runs some Docker containers. It installs like different versions of TLS libraries and tools and hit this endpoint to generate those fingerprints. So it does this automatically, and like in a few minutes, you can generate a huge data set. So what's the use cases? Like if at this point you're still not sure what is the real use case of this, as I said, it was just a fun for me. I didn't want to implement the JA3 fingerprinting and other fingerprintings into all the honeypots that I'm using upstream. I was like, okay, what if I just create this reverse proxy and log all those at that point instead of implementing that at different honeypots that I'm using? So that was the main use case for me. And then I wanted to just dynamically mute or silence the annoying bots, because like last year I set up this API LLM usage like $20 per month, and I used my like obviously LLM-based honeypot. So although I had this usage limit, but someone hit my honeypot like with 100,000 times in like 5 minutes, which used all my budget for the month. And it actually proves that that honeypot was actually useful, because the reason they hit my honeypot that hard was they thought it's an open proxy. Like they wanted to use it as some sort of like ad fraud. So they just generated traffic that way, because the way my honeypot responded to their request made it look like it's an open proxy. With static honeypot, you couldn't do that unless you knew about like these patterns before. But yeah, for other use cases, you can just deny unwanted traffics. Like you don't like wasting your resources on random sketchy bots, which just crawls through your website or server. Things like that. You can route traffics which match with Suricata to honeypots to learn more about them instead of letting them hit your application. And yeah, just targeting scanners is another good one. So just slow them down. Okay, so one last bit before we finish the talk is about the agents. So I had this section about the agents, which I first say like, okay, agents are basically just LLM plus tools plus instructions. That's it. And they run just in a loop. They just observe, act, they like do it again and again until they're satisfied with the result. So I created this experimental agent you can see in the repo later today. Right now, I just included the report it generated last night with the new OpenAI model like GPT-5, which is amazing. Like it just went through 10 megabytes of logs I provided, like the exact same log I analyzed like 7 years ago. Like the same patterns I was just talking about the jaw trees, like rotating jaw trees. As I said, I accidentally found that. So I just wanted to experiment to see if they can find it, like the AI agent can find it, and it actually found it like in 1 minute in like 10 or 20 megabytes of the logs without providing any additional context. So the only thing I provided as instruction was analyze the attached JSON log, and that's it. So yeah, it was exactly the first thing it found about that JA3 rotation. One thing I wanted to share was don't just throw data to LLM and expect it to analyze. It just lies to you. Like even if it says like, yeah, I did it, it didn't do anything. That's exactly the point of like how to use LLMs. I wanted to just use this as an example to show you if you want to use LLMs on agents in general for log analysis, for investigation or things like that. This is like a hot topic. I guess probably we have like hundreds of talks right now and startups and products out there doing this. But how do you know that when the LLM tells you that it did something, it actually did that? I'm sure in a lot of cases it didn't do. So the key is to use Python tool use, or let the LLM use the interpreter, so it can actually just like a human, which like, how do you analyze a 10 megabyte log? Do you just scroll through it? No, you just like probably use Python or bash scripts or something to just analyze, find patterns, aggregate, do all things. So without providing that to the LLM, how you expect it to do all these things? So in my experimentation, the AI agent I created, the only tool I gave the LLM to use was just the interpreter, like it's called interpreter in OpenAI API, but it's basically just the Python tool use. It just spins off like a container in the clouds and uploads the data and let the tool just do whatever it wants for analyzing it. I uploaded the full investigation into the repo, so you can see the summary of the investigation and also the entire chain of thought, which is very interesting. Like I was looking at that, I was like, if I want to do this, like it takes me hours, and I still don't do all these like queries. So it's probably done like 40 or 50 different queries and aggregations with, I guess, pandas or something like that, and data frames, and analyzed the logs and generated the result. And then the rest of demo, I was showing that based on this analysis, it automatically uses another sub-agent to create these block rules for Finch, and it just applies the block rule based on the like foundings and using the admin API. So the case happened to me last year on like the attacker used all my $20 like usage. Can't happen with this agent thing, because like it just like subscribe to that stream. If it finds this stream, it just like this pattern, it just applies a block rule. So I guess I had a few other demos, so it's useless talking through it. So I would instead like open the stage to you if you have any questions. Otherwise, I'm here after the talk and we can like talk about all these things like AI agents, fingerprints, and reverse proxies. Thank you.